This is XGBoost for cyber defense. 18 episodes for the people who actually ship detections, the ML, detection, and SOC engineers who have to make a wall of red trustworthy. Here's the promise. By the end, you can stand up a detector that holds up in production, calibrated, constrained, explained, monitored, hardened, and tiered. And we get there along one spine: detect, explain, operate, defend, ship. First, we detect phishing URLs, malware, intrusions, DGA domains. Then we explain every alert with SHAP so a human can trust it. Then we operate: precision floors, cost optimal thresholds, a false positive budget. Then we defend against drift and evasion with threat model priors baked in. And finally, we ship the whole thing as a tiered SOK pipeline. Every world is seeded in code, no downloads, no Kaggle, runs in Colab, reproduces to the digit. And we measure honestly PRIUC, recall at a fixed false positive rate, never accuracy alone. So, episode 1. Here's the very first decision a detection engineer faces. You've got a wide table: malicious connections versus benign, 28 features, 12,000 rows, and attacks are a thin slice, about 1 in 6. The reflex of the decade is throw a neural net at it. Today, we kill that reflex with a chart, not an opinion. The misconception we're executing first: deep learning is always better. It is not here. Security telemetry isn't pixels or tokens. It's a short, wide, mixed type table where attacks are rare. That's the home turf of decision trees, not of a hungry MLP that wants a million rows. The number that settles it is coming in a bar chart, and the neural net loses it. Look at the data the way a detector does. 10 columns: duration, bytes in and out, packet counts, SYN ratio, port spread, failed connections, TLS version, geo risk, ASN reputation. Different units, different scales, some nearly categorical. A tree doesn't care. It splits on failed cons, 7, and SYN ratio, 0.6 directly, no normalization, no embedding. That indifference to scale is the first reason trees win on telemetry. Now the imbalance. Benign traffic is roughly 85% of the rows, attacks the rest. A single deep decision tree memorizes the majority and grows brittle branches for the rest. It scores PRAIUC 0.461, by far the worst of the 4, and at a real operating point, it cries wolf on nearly half of benign traffic. One tree overfits. That's not a bug you tune away, it's the method. So we stop trusting one tree and let many trees correct each other. Boosting trains trees in sequence. Each new tree fits the errors the previous ones made on the hard examples, which on imbalanced data are the attacks. That focus on residual mistakes is why XGBoost climbs to 0.780, while the lone tree sits at 0.461. And the number that actually ships, it holds the lowest false positive rate of any model at the same recall. And the MLP, it's the twist. At 0.717, it actually edges the random forest on ranking, but it still loses to boosting it costs the most, scaling 400 epochs, a learning rate to babysit. And at the recall a SOC runs, it fires more false alarms than XGBoost. 12,000 rows is a snack, not a meal, for a neural net. More parameters bought a tie on the ranking, and a loss on the metric that pages an analyst. One honest note before the punchline: we judge with PRAUC, not accuracy. On a 15% attack table, a model that screams benign at everything scores 85% accuracy and catches 0 intrusions. Accuracy is the lie we debunk properly in episode 04. For now, just trust the area under the precision recall curve, because it only rewards catching the rare class. The verdict on one screen: decision tree 0.461, random forest 0.762, MLP 0.777, XGBoost 0.780, same split, same features, 0 tuning. XGBoost takes the top PRAUC and the lowest false positive rate at the recall a SOC runs. The lone tree collapses. The net merely ties the ranking at triple the cost. Boosted trees win the cold start. That's the whole thesis of this course. On security tables, start here. Let's watch the code that produces those 4 bars. Open O1 ytreeswin.py. Top to bottom, it builds one seeded world, trains 4 models on the exact same split, and prints the 4 PRAICs that become the bar chart. Nothing fabricated, the figure is the print. First, the world. Make classification with 12,000 rows, 28 features, 10 informative, weights 8515, random, state the 7. Then we rename the columns to real connection telemetry, duration, bytes in, bytes out, PKTs, SYN ratio, unique ports, failed cons, TLS version, georisk, ASN rep. Same numbers, security real names. One split, stratify, so the 15% attack rate survives into both train and test. Random, state then 7. Every model sees identical rows. That's what makes the bars a fair race instead of 4 different experiments. The 4 contestants, each at same defaults, decision tree classifier, max depth 6, the lone tree, MLP classifier with 2 hidden layers on a standard scaled copy, because neural nets need scaled inputs and trees don't, random forest, an XGB classifier with scale pose weight set to the benign attack ratio so the gradient leans toward the rare class, the one security knob we turn even in episode 01. Scoring. We never call .predict for the metric, we take predict proba, the attack probability, and feed it to average precision score, which is PRAOS. That's the security honest number. It measures how well the score ranks attacks above benigns, and it ignores the easy 85% of benign traffic that would inflate accuracy. The print loop drops 4 lines, decision tree 0.461, random forest 0.762, MLP 0.777, XGBoost 0.780, and the very same 4 floats drive the bar heights. Figure equals terminal equals the headline on screen. By construction, XGBoost's bar wears the threat red cap and the sim ship this tag. So the first lesson ships on wide imbalanced mixed type telemetry. Gradient boosted trees win the cold start. Start here, not with a neural net, but a chart of 4 PRAOCs is a lab result, not a detector. Next episode we build the one we'll live with all series long. The phishing URL classifier end-to-end seed 42, the recurring house on dataset every later episode reuses. That's where the honest baseline gets its name.